Computer audio. There we go, up and running. All right, so I decided I'd do a lecture on quadratics. I'm kind of a little pressed for time. Got a marker? Yeah, I got a marker that works. I got an eraser. Okay, we're good. And so this lecture is going to encompass, I hope, kind of a starting from scratch, what's going on, what are quadratics, how do we work with them? And then may not be able to say everything I want about quadratics, but there'll be a part two where we start to look at factoring and solving equations with quadratics. And could be about 20 minutes, I think, part one, and then we'll see what I end up doing with part two. But yeah, make sure you watch part one here. So let's get started with it. I've got some squares. That's what quadratics are. They're four-sided figures, right? They're rectangles, and sometimes they're squares. And when you see x times x, x squared, you know you're working with a numerical trajectory, kind of what you see here. The side length of a square is -3. You know, physically can't be a negative, but -3 times -3 is 9. So we really have input of a side length, which is an x to the 1. Right? And all these equations in graphing form have x to the 1 in the parentheses, but then we're squaring, and we can see that sometimes a bar graph is helpful. So if this is 9 units, I'm just calling it 9, and that's 4, and that's 1, and then that's 0, and then it's 1 again, 4 again, 9. We can see it's not linear. You know, it's not the same rate of change. From 0 to 1 is 1 unit of change, 1 unit vertical. 1 to 2 is 1 unit of change, but 4 units vertical. Now, it's not the same. And hopefully we can see that trajectory, that cup-shaped trajectory. And if you did it in table form, you can see that you're decreasing, the areas are decreasing, 9 to 4 to 1, and the graph is decreasing. And so maybe that helps you read graphs a little bit better. So moving right along, we have calculations, second degree calculations, two-dimensional pictures, ax squared plus bx plus c, and all of a sudden we got these other terms here that affect the numerics, affect the put this x in, get this y out. And what that does is it moves the graph around. And I'm going to try to explain why. We sometimes refer to local behavior and end behavior. And the biggest term in a polynomial determines end behavior. In order to see that, I think we need some numbers. So I've put some numbers down over here, and I've given a specific, should have had some tables already ready here. All right, I should have already had this done. Let's get this chair out of it. Make sure you can see everything. Yeah, I think we're pretty good here. All right, so I decided to look at -2x squared plus 12x plus 7. Just going to play with that calculation. What I'm suggesting is that you rewrite it from local behavior. Local behavior is when the numbers are small, right? Like 0. It's about as local as you can get in a graph, you know, and you're near the origin. And then end behavior, I thought I'd work with the number 100. And I thought I'd work with, hey, what about, where's this graph going initially? I just picked a number that's a little bit bigger than 0. To give me a sense of, is the next answer positive or negative? I thought we'd play with it. So you put a 0 in, and 7 is still 7, hasn't changed. 12 times 0 is 0, and -2 times 0 squared is -0. Looks like you get 7. So I'll draw a y-axis over here, and I'll just put a 0 gets me 7. Now, I wonder if I'm going up or going down from there. Well, to find out, I do a small change in x. And if I do this, 7 still remains 7. That's a constant. I don't care what x we use here. That's not changing. That column's not changing. This one does. This one changes by 12 times this means that 12 times that gives me 0.0012. 0.0012. And now over here, I'm going to subtract. Well, I know if I square that, it's got 4 decimals. If I square it, it's going to have 8 decimal places. 8. And then I got to multiply that number by 2. Boy, that's going to become 0.1, 2, 3, 4, 5, 6, 7, 8 decimal places. That's a pretty darn small number. In fact, it's 4 decimal places smaller than this number. So it's 10, 100, 1,000. This is 10,000 times, well, because it's times 2, little factor up, but basically it's 10,000 times smaller than this. I think we can pretty much ignore this because this is telling me that I'm going up from 7. This is a much bigger number than that. So I'm going up bigger than 7. And in fact, that's so small. And NASA works with 8 decimal places for accuracy, and they're putting people out in space. So let's look at the change in X. So let's look at the change in this column. 7 to 7. How's that changing? If you think this number is different than that, after class tomorrow, I just want to talk to you briefly. Just stick around a little bit, and we're going to take a little walk. Just a little walk up the hill, okay? And behind the dining hall, where there's some nice people. We're going to talk to some nice people there, okay? No change here. The change is being dominated by this middle term. And I'm going to compute the change by taking this y value, the change in that y value, and I'm going to divide it by the change in the x, which is 0.0001. And that's going to move the decimal place. I'm just doing division here, right? So it actually, this goes into that 12 times. Oh, it goes 12 times. That means at that little change, I'm going up at 12 to 1. And I'll just show it. All right. I'm just showing. I'm going up. And I know the end behavior. Let's look at it numerically. Let's take a big number now. 100. Well, again, if you see that change, stay after class. If I multiply that by 100, I get 1,200. And if I square 100, I get 4 zeros. That's 10,000 times minus 2. That's minus 20,000. Geez, I wonder in this numerical tug of war, which term is dominant now? Yeah, I think that's giving me end behavior, which means that on the left side, down, on the right side, down, when I start picking big numbers, whew, this thing is headed south. So it must look like this. It's got to look like that. And I know that immediately. I know the y-intercept, and I know which direction I'm going, and I know the shape of the graph. So I don't have to do this again. I can immediately label the y-intercept and do that. With practice, you will too. So then the question is, what's the x and the y of the vertex? And why? Well, let's see if we can answer that over here. I mean, I can answer it now. Can you? We actually have done it in class. You're going to do what? Pick minus b over 2a for the x. It should be a positive number or we've done something wrong. There's b, 12, so I'm going to do minus b, which is minus 12, the opposite of this. And I'm going to double this number. That's negative 4. That tells me that 3 is the x that gets me a maximum. I mean, x squared get us a minimum over there. I forgot to say that, right? I had it there to remind me. But these graphs, right, have a minimum. And when do you have a minimum? When there's no area. That happens when x is 0. All right, so hopefully you saw that, and I held the camera, held the computer properly. Almost went down on that. All right, so all I got to do is find the y value that goes with 3. Oh yeah, I got an equation that finds y value as long as I know my x and I know my x. So I'm going to plug it in, minus 18, the next is 36 without looking, because this is always twice that, opposite, always, otherwise you pick the wrong number. So this is 18 plus 7, which is 25. Yeah, 25 is bigger than 7. It should be above 7, and 3 is to the right of 0. Looks good to me. Yeah, looks good to me. Now, what else have we been doing in class? Well, I've been giving you, as a skill, No, what are we doing? We're writing these equations based on the graph you see. Right now I got graphing form. I can expand it. I can find the roots. You can do all of it in under 60 seconds. God, it takes 30 seconds just to write the quadratic formula. You can get all those answers right now, probably 20 seconds. But it's going to take some practice. All right, so what do I know? I know that 3 gets me 25, and I'm looking at change in area. And I know if my side length changed by 3, then the area of the side of the square is 3, and 3 squared is 9. So that's what happens when I put 0 in here. I get 9 units. And 9 plus 25 does not take me to 7. No. If I go backwards 3 units in square, I should have gone up 9. Should have gone up 9. But I didn't go up 9. I went down 18. Well, geez, that's -2. And I know what x minus 3 squared is. X minus 3. You'll have to do this out for a while. You got to do that out for a while, but you've got x squared minus 3x plus 9. Right, so let's look at what this is and see if we could get this answer in here without having to do any of that. Well, what do you see? I see x squared. Okay, I see x squared. What do you see? You see a 9. Well, 9 is 3 squared is 9. I think I can learn to do that part. Then the only thing I got to do is get the middle term. And it looks like there's 2 of these things, 2 of these minus 3x's. Well, if I multiply -3 times x, I get minus 3x. All I got to do is double it. Now I'm not working so hard. I put in the effort so I can do it effortlessly. And then the last thing I got to do is add 25. Right? And I'm going to put that 2. I'm going to call this -2 to get it out of the way so it's still here. And so what do we get? We get y equals -2x squared plus 12x minus 18 plus 25 happens to be 7. And I want you to learn how to do that, how to square this binomial, multiply it by -2 and add 25. That'll be on your test. All right, and so there we go right back to the beginning, right where we were. All right, so now let's talk about creation of vertices. Let's start with a kind of a term that you saw today in class. You saw x squared plus 6x in class. And what were we doing with x squared plus 6x? We were factoring it, writing it as a product. All right, x times x plus 6. That's a product. Well, I think there are 2 famous products that come to my mind without any hesitation. All right, can you think of a famous product? Well, length times width. I think it's famous because the whole discipline of mathematics is based on rectangles. I mean, maybe I can't say everything, but a whole lot of it, certainly up to the point that I've studied. Now, once we get past that, which is, you work in college, I might have a different answer for you. But right now, rectangles are it. Calculus is an accumulation of little thin rectangles under a curve. And the rate at which the curve is changing, the original curve is changing is a lot to do with layering process. And layering process is, here's a square, there's area. If I want more area, I just draw another lengthened, square, 2 sides. I just draw 2 side lengths. I attach it. And I'm not going to get into calculus right now, but the discussion continues. All right, so now I have this calculation, which means that I can write this that way. Well, let's see if we can by using some numbers. Okay, x squared, let's put a 0 in. Oh, we get 0 out. Let's put a 0 in over here. 0 times x times x plus 6. X times x plus 6. Okay, so I pick 0, and I get 0 times 0 plus 6. Yeah, I think that's 0 too. Geez, I wonder if it works for all numbers. Let me try the number 10. 10 squared is 100 plus 60. Now let's put 10 in over here. 10 times 10 plus 6. That's 10 times 16. Yeah, 160. Sure seems to be working for all numbers. I guess I can make that statement. But not only is 0 important, but I think -6 is important too. I think that's a critical number. -6. -6 squared is 36. And 6 times -36 is -36. Boy, if I put -6 in, I get 0. Over here, let's put -6 in. -6 should be above that, but let's put it in there. So that's -6 times -6 plus 6. Well, I know what -6 plus 6 is. That's 0. And 0 times anything is 0. Okay. I said length times width, to me, is the most famous product. The other one is rate times time. Rate times time, getting amounts. So let's look at length times width. Let's look at this in the context of length times width. All right, so geometrically, here's 6 units. I decided to call that 1 unit of measurement. X could be anything, could be bigger than this, but I'm just standardizing this. So this is an area of x squared, and this is x times 1, right? That's x times 1, that's x, that's x, that's x. And I think I can add those up. And if I do, I think I got 6 of them. All right, so x times x plus 6 is x squared plus 6x, because those are like terms. Right? So that's what this area is, x squared plus 6x. So for instance, if x was 10, that would be 10, because we already did 10, right? 10 times 10 gets us 100 units, and 6 times 10 gets me 60. Well, there's the table value we had over there a while ago, 160. But the problem with solving these equations, one of the reasons we learned to change the way this is written is this is the calculation under consideration. That's the major operation. And what we use to solve equations, 90% of the equations we solve, we use inverse operations. Well, the inverse operations of squaring is using a square root. But I don't think I can use a square root unless the rectangle is a square. By definition, if this square has an area of 9, then its square root is 3, and 3 happens to be the length of the side of that square, which tells me the length of the side of a square is the square root of the area. Which means that if I had a 7 in here, then that's the square root of 7, and whatever that is as a decimal times itself is going to get me 7. I'm going to use that later in the term too. All right, so where was I? Oh yeah, so mathematicians can't solve these equations when they're written this way. They have to change them by either factoring and setting to 0, and then you got a shot at it, or you got to do something else, and it's the something else that I'm going to talk about right now. In fact, this will not be a this will be a part 1 and a part 2. And part 1, I'm ending this in a little while. Going to get some practice over there. Okay. All right. But this is what you need to know conceptually, is how to change a rectangle into a square. Okay. And so I'm going to do this now up here. Started over here. And I'm going to write that as 6 now. I shouldn't have done that. Let's go back to this. Okay, each of these is an x, an x, an x, an x, an x, an x, and an x. Okay, so what am I going to do? Well, this is 6x here. This is x squared. Oh, no, excuse me. This is just plus 6. Okay, well, what mathematicians did is they took some of the units off the longer side and put them on the shorter. So to even this off, mathematicians, let's see, that goes there. All right, so that's there, that's there. That should be pretty good. So what I'm doing is I'm taking these 3 and I'm putting them here. Well, no. How do I explain this? Anyway, x plus 3, x plus 3. Because that gets me x squared plus 6x plus 9. And remember, we want x squared plus 6x. But I got the marker. I can just get rid of the 9, just numerically, right? This is just a number. I just got rid of it, which leaves that numerically. So what I've basically done is what's called completing the square, x plus 3 squared minus 9. And I'm suggesting that we're not going to draw these. We're not going to do it that way. We're not going to do it the textbook way, because I guess I got to explain why that equals 0, and you can see these numbers pretty quickly, 0, -6. All right, so I got a 0, a -6, and I know I got a x squared, which is cup shape up, right? Cup shape up, and it's that number right in the middle that gets us our minimum, which is the average of the roots. So let's look at the general situation. Trying not to lose you. It might be losing you right now. It takes a while to understand this. Right after this section, we're going to do 4 or 5 problems in a row real quick, rapid fire, so that you can learn how to sketch and write the vertex and the y-intercept and be done with it in 10 seconds, and have to do it effortlessly would be nice, because then you don't have to think. Okay. So I factored this, x times ax plus b, x times ax, ax squared, x times b, bx. I set it to 0, so I know one of my answers is that one is 0. And then I solve ax plus b equals 0 by moving the b to the other side, negative b, and then dividing by a. And we know we've got cup shapes up or down, but what's right in the middle is the average of these two numbers. So I added those two numbers up and divided by 2. That's basically minus b over a divided by 2. When you divide by 2, you're really multiplying something by a half. And there's your minus b over 2a, which I didn't have the camera on too well. So let me get that part again. So ax plus b equals 0. You saw that. So here's minus b over a plus 0. That's what I said, but you couldn't see it. So adding 0 is really just dividing minus b over a divided by 2, which is the same as multiplying something by a half. And then you get that famous relationship of lettering minus b over 2a. And for those of you who work with the quadratic formula, they probably drilled you with it. You got minus b plus or minus the square root of b squared minus 4ac over 2a. And I hope you can see the minus b over 2a there. Okay. All right. So now that we know that, then we can start to do some work more easily. So I'm going to do that now. I probably forgot to say something, but I'm getting pooped. All right. So, our goal is to be able to graph these things quickly. And what I'm suggesting is start with just a y-axis and rewrite this backwards. Oh, minus 20x plus 2x squared. Can we agree 2x squared is a cup shape up? We know that. Okay. So I'm going to start with 3. So if I put a 0 in, I get 3 out. Put a 0 in, those terms cancel. I know I'm going down at 20 to 1 from the work we did before. And if it's cup shape up, then it's got to look like this. And the only thing I'm missing is the x-axis, the vertex. And I know how to get the x value now. It's the average of the roots, which can be found by minus b over 2a. So minus b, positive 20. Over 2 times a. A is 2. 2 times 2 is 4. So I now know that that's a 5. And if I want to find the y value, all I got to do is plug it in. So that's a 3 minus 100. If that's minus 100, then this has got to be plus 200. No, it's not. What did I just say? 5 times minus 20x. Oh, because I'm doing it backwards. I'm so used to doing it here. 5 squared is 25 times 2 is 50 minus 5 times this 100, right? So now I'm doing it backwards. Oh God, I haven't done that in such a long time. All right, so this is half of that in this direction, and change the sign. That was a little odd, because I've done this for years and years and years in that direction, because I kind of know what I'm looking at here. But so I guess you're going to learn it if I keep doing it this way. minus 100, that's minus 50. 3 minus 50 is negative 47. Okay. And one more time, let's practice what I'm asking you to do. Write it in graphing form. All right, so if I want to write this in graphing form, I hope you can see that that gets you the first term, right? Doesn't 2x squared come from 2x squared? And if you got a 5 here, you're going to write minus 5 because we're trying to get 2 zeros squared to either get a maximum or a minimum. Right? So if 5 is the key number, you got to make it into a 0. That does it. That gives you the minimum. And if you got a 5, you can plug it in. I like to work with 0 personally, but put 5 in, and if you put 5 in, we did it a minute ago, you get minus 47. So I'm not going to do it again. Okay. And you got the roots staring you in the face. Roots are, when does this thing hit a height of 0? That's what roots are, is when you produce a 0. Well, what would you have to do? You'd have to go up 47 units. I'm not going to do this again this time. You're multiplying something by 2, so you're going to have to divide by 2. Then you're taking a square root, so you got to do the inverse of squaring. And these x's are the same distance from 5. And that's the distance you got to travel. So really, you got everything at your fingertips if you can just show the graph. Now, what I just did was, I set the thing to 0. Right? Okay, how do you solve that? Don't you go up 47? Subtraction, and isn't that what you have to do? Don't you have to go up 47? And this is the number 5. Don't you have to go in the positive direction and in the negative direction from there? Okay, and that's going to show up here in a minute. So right now we're here. What's the next thing we do? I think we divide by 2. If we said that a second ago. Then you got to undo squaring. Right? There's 2 parts to this. Right? There's one on the left and there's one on the right. That's why the plus minus is there. And then minus 5. So right now we're at x minus 5. So x is equal to 5 plus or minus the square root of 47 halves. Right? Now I'm not going to do that. I'm going to do that in part 2. Talk about how do you solve quadratics and what the tricks are. It's a longer conversation. I'm getting tired. You probably are too. Bear with me just a little bit to practice this 2 more times, just to get you a few reps. So textbook problems. First one I'm going to give you. See if I'm missing anything here. No. 10 after 10. All right. Let's do a negative. Minus 3x squared. Let's keep it simple. Plus 12x. And let's do minus plus 9. All right. That's a quadratic. So first thing we're going to do is change it to be y equals 9. We're going to work in this direction. All right. So I'm not going to rewrite. I'm just going to work in that direction. So that's my y-intercept. 0, 9. Am I going up or down from there? That's positive. I'm going up 12 to 1 at that instant. All right. And it's cup shaped down. So I now know that. All right. So all I got to do is find the vertex. Do you remember how? Minus b over 2 times a. Negative into a negative is a positive. That sure looks like the number 2. Okay. How do I get the y value? I plug 2 in. Oh, good. I don't have to be dyslexic anymore. 2 squared is 4 times negative 3 is negative 12. 2 times 12 is 24. There's my 2 to 1 ratio and opposite. So I know that number's right. And I'm adding 9. So that's 12 plus 9. That's 21. Okay. So let's get this from the graph. Okay. Pretend you don't see this. How do I work this from the graph? Well, I got the vertex, 221. So I know I can write x minus 2 squared plus 21. Now I know that from 0 to 2 is two units of change on a square. Well, 2 units squared is 4. And if I put a 0 in here now, 0 minus 2 is minus 2 squared is 4. I got to cancel that out because that number plus 21 doesn't work. I got to get from 21 to 9, which is down 12. Oh yeah, that's minus 3. And minus 3, here's your chance to square a binomial again. without having to write it on paper. I hope you remember you gotta square that. You gotta square that. Right, so there's x squared, and there's 4. And minus 2x is gonna show up twice. So there's minus 4x, and then you're gonna add 21. What do you get when you do minus 3 times x squared? Minus 3x squared, yay! What do you get when you do minus 3 times minus 4? 12x, yay! What do you get when you do minus 3 times 4? Minus 12, minus 12, plus 21 is 9. Oh, guess we're cooking with gas. Well, if I make a minus 3 here, boy, I can solve this for 0 real easy. 21 becomes minus 21, it's gone. Division by negative 3 becomes 7, it's gone, it's gone. Squaring becomes square rooting, boom, it's there. And now, minus 2 becomes positive 2. I'm going to show you if that works, going to show you how it works. That's going to be the end of the video. So I'm going to go back to graphing form. Minus 3 times x minus 2 squared plus 21. And I'm going to put that answer in and see if we get 0. My answer is 2 plus minus the square root of 7. Do you mind if I do the parentheses first and I do 2 minus 2? Oh, that cancels. Is it okay if I square a positive? That gets me a positive. If I square a negative, that gets me a positive. I guess this is a positive number, and I guess I'm going to have to square the root 7 now. Oh, yes. Oh, yes. By definition, we said square root of 7 times square root of 7 is square root, and that gets you 7. So I'm going to get 7 out of this when I square. I think I know what 3 times negative 7 is. I think it's negative 21. And I think I know what negative 21 plus 21 is. I hope I captured most of that. I'm too tired to do it again. All right, but that's just look at what's going on. And I didn't want to do that in class. For God's sakes, half of you would be, I do you in. But this, you can replay different parts. I suggest you do until it makes some sense to you. 5 minutes here, 5 minutes there. Then you'll know what you're doing and why. That's always important. I've got to tell you why you study math, and we'll do that next week. I think I got a good answer for you. So why we study math. We'll maybe do that next Wednesday or Thursday, because it's important for you to know why you're studying math. All right. So that's the end of this video. I don't know how long that took. And I won't be doing this to you every night, but early on, yeah, I got to put some stuff in your window of opportunity to learn. That's a window. It's a rectangular window. It's a screen. Oh, wait a minute. I'm starting to lose my mind. There we go. End of video.